Hello everyone. In this video, we will look at conditional distribution and joint distribution of random variables. Let's start with the conditional distribution. For consider that we have two events A and B, and you have seen previously the conditional probability of A given B is written as P of A given B, which is equal to probability of A and B divided by probability of B. Now this can be extended to a random variable x and some event b involving the random variable, and it's written as the CDF f of x given b, which is equal to the probability of the random variable x less than or equal to small x given the event b. Using the same definition of conditional distribution that we use for probability, we can write that this is equivalent to probability of x less than or equal to some value of small x and b divided by the probability of b when probability of b is not equal to 0. That means b, the event, has to occur. The properties for the conditional CDF in this case are similar to the CDF cases we have seen before, both for discrete and continuous. Since it's a probability, the value has to be between 0 and 1, and if x takes a value infinity, then the probability is 1. For minus infinity, the probability is 0. And the PDF of x given b is differentiation of the CDF, similar to what we saw in the continuous case. And similar to the normal probability without conditioning, the probability for random variable x taking values between small a and b given capital B is equal to the CDF at b given the event b, capital B, minus the CDF of x at a given the event b, which can also be written in terms of the PDF. So integrating the PDF between a and b. So this is similar to the normal case without conditioning. The only addition here is you have a conditioning over the event b. Now let's look at an example. Let x be a continuous random variable with the CDF capital F, and consider an event b equal to the random variable x less than or equal to b. Now let's determine the conditional CDF. Now in this problem we can divide it into two cases where the value x is less than or equal to b, or it's greater than b. So first look at the general case for the conditional CDF. So the CDF can be written as we saw before, probability of random variable x less than or equal to small x and b divided by probability of b. And if we expand what the event b is, it's random variable x less than or equal to b. So we have these two events together divided by the probability of x less than or equal to b, which is pb. Now this can be written as probability of random variable x less than or equal to small x and probability of x less than or equal to b, and this is simply the CDF f of b. That's the by definition. So from here we consider two cases when x is less than b and x is greater than b. So when x is less than b, that means small x is less than or equal to small b, then this reduces to f of probability of x or random variable x less than or equal to x, because x is smaller than b, so when you consider both of them together, then only this is true. So the probability of random variable x taking a value less than or equal to small x is f, or the CDF of x at x by definition. Now consider the case of x greater than b. So if x is greater than b, then only this can be true. So the numerator reduces to probability of random variable x less than or equal to b divided by f of b, and these two are the same. So this will be 1. So when x is greater than b, the CDF becomes 1, and it can be plotted here. So x-axis is the value small x, y-axis is the probability. So if this is the general CDF of x, then the CDF of x given b will be more than fx, because this is a probability, which is between 0 to 1. So this has to be more than fx. But when x is equal to or more than b, then it will become 1. So the new CDF is this. Now let's look at a vector of random variable. So far we have been looking at a single random variable, but now consider more than one random variable for a given sample space. Now it's important because there are many cases, real life scenarios, where we come across multiple random variables. For example, in navigation, the location of object has to be represented with 3 coordinates x, y, z, each can be a random variable. So the position can be an outcome in sample space, but that sample space will have 3 coordinates, which can be represented by 3 random variables. Similarly, images can be represented with 3 colors, red, green, and blue. So many times it's convenient to use a vector of random variables where each component is a random variable. Now the concept that we have seen so far for a single random variable can be extended to multiple random variables, and we'll see how. The concept we'll be showing next will be using 2 random variables, but it can be extended to a sequence of n random variables as well. The same concepts apply. So consider 2 random variables x and y in a sample space S. Then in 2D, it is a function, x and y is a function that assigns a point small x and y to each outcome in S. And the range is given by this, which pictorially can be represented as the sample space S, and each outcome is mapped to a 2D sample, x and y. So both x and y are real numbers, and they can be discrete or continuous or mixed, depending on how capital X and capital Y are defined. So for joint random variables, we can define the joint cumulative distribution function, which is denoted by capital F xy, and this is equal to the probability of random variable x taking a value less than or equal to x, and random variable y taking a value less than or equal to y. So the joint CDF is the probability of the event that both of these occur. Now if x and y are independent, then similar to the probability case, the CDF of x and y can be written as CDF of x times CDF of y. The properties of the joint CDF are similar to the properties of the single random variable. So if 1 is minus infinity, then this is an impossible outcome, so the probability will be 0, and f of x and y both at infinity will be 1. the probability of random variable x between a and b given y is less than small y is the CDF at by minus the CDF at ay. The same concept applies to random variable x, and when you consider that for both x and y. The probability distribution for the joint random variable is given as this. When they are discrete, it's the probability mass function. So small f of xy is equal to probability of x is equal to small x, and y is equal to small y. And for a discrete case, since it's a probability, it's a positive number for all x and y, and it has to sum to 1 for all possible values small x and y. If x and y are continuous random variables, then the PDF can be written in terms of CDF as the differentiation, partial differentiation of the CDF with respect to x and y. The properties of the PDF for the joint case is similar to the single random variable case. So it is positive number, and the integration for the entire range has to be 1. It's a continuous function, and the probability of x and y defined over a given event is the integration of the PDF over that event space. And similarly, if x and y between some values a, b, c, d is defined like this, where you integrate the joint PDF over the ranges a, b, and c, d. So it's now double integration. The mean of two random variables can also be defined. So if the joint distribution of the PDF is f of xy, then the mean of the random variable g of xy is defined like this for the discrete case and like this for the continuous case. So it's similar to the single random variable case, except we replace the PDF with the joint PDF, and we have two sums or two integrals. Now in the joint case, for two random variables x and y, they are independent if the CDF of x, y, the joint CDF can be written as the multiplication of the individual CDF. We saw that before already. The same applies to the PDF as well. So the joint PDF is equal to the multiplication of the individual PDFs or PMFs. The mean or expectation of the multiplication of the random variables xy when they are independent is equivalent to the product of the individual expectations. And if x and y are independent, the variance of ax plus by is written as a square times variance of x plus b square times variance of y. Now if you have joint distribution of x and y, you can easily get the individual distributions of x and y from the joint distribution, and that is called the marginal distribution. The marginal probability mass function of x, if we denote it as g of x, can be calculated from the joint distribution as g of x is sum over all possible values of y of the joint probability mass function. So we are summing over all values of y, so we get g of x, which is the probability mass function of x. Similarly, for the continuous case, we integrate it over all values of y to get the PDF of x from the joint PDF. We can extend the same formula if we need to calculate the marginal distribution of y instead of x. So we represent that as h of y, For example, we don't have to represent it as h, but here we have h. So h of y is equal to the sum of the PMF, the joint PMF over all possible value of x, and for continuous cases integration. So that's the marginal distribution calculated from the joint distribution. We can also write conditional distribution for two random variables x and y. Earlier we saw conditional distribution for the random variable over some event, but we can also calculate the conditional distribution of two random variables. So the distribution of x given the random variable y is the joint distribution of the random variables x, y divided by the distribution of y. And the properties for this joint or conditional PDF or PMF are similar to the unconditional PDF or PMF. We can also calculate the conditional expectation from this conditional distribution. So for the discrete case, E of x given y is equal to sum of x times the PMF, the conditional PMF. And for the continuous case, similarly, the expectation of x given y is integration of x times the conditional PDF of x given y. Next, we'll look at the sum of random variables. So if we have two random variables, then the sum we can easily calculate. And it's important because it has many practical applications. For example, when x, for example, is a random signal voltage you're getting from some sensor, and y is the noise, and usually it's additive noise, so you get the voltage as x plus y. Now if you consider z as the sum of x plus y, where x and y are both random variables, then the probability distribution of the sum is the convolution of the individual distributions. We'll see what it means. So for the discrete case, the probability mass function of the sum is given as sum over all values of x for the joint PMF. Probability of x is equal to x and y is equal to z minus x, because x plus y is z, so y can be written as z minus x, and this sum is called the convolution sum. And the sum is taken over all values of x that satisfy the equation x plus y equal to z. This can also be done for the continuous case, so the sum is replaced by the integration, so the PDF of the sum is equal to the integration of the PDF of x times the PDF of y at z minus x, because x plus y is equal to z. And the integration again is taken over the entire range of values of x. Now this concept of sum of random variables can be extended into n random variables. So it need not be 2, it can be more than 2. And that leads us to the central limit theorem. So if you consider n independent and identically distributed random variables with mean mu and standard deviation sigma, and the sum is the sum of these random variables, then what the central limit theorem states is that the distribution of the sum of these n identical and independent random variables approaches a normal distribution with mean mu and standard deviation sigma over square root of n as n becomes large. So what it means is that if you have n independent and let's say identically distributed random variables and you add them all up, then the resulting random variable will have a normal distribution when n is large. And the CLT guarantees that. So the proof shows that the sum of these random variables is indeed a normal random variable. Now here we're considering xi's to be from the same distribution, but even if they are not the same distribution and still that if they're independent, then the sum still approaches an approximate normal distribution with large n. So it's a very important concept that has many practical uses. So central limit theorem basically says that if you add a bunch of random variables that are independent, then you'll get a normal, then you get a random variable that has normal distribution. So this brings us to the end of this video. We looked at conditional distributions, joint distributions, and the marginal distributions.